Assalamualaikum and good day. Dr. Raihan and Dr. Adila, and this is our integrated design project combining both reaction engineering 1 and separation process 2. Moving on, this is the members of Group B. We have Aisha Vidati, we have Ayman Akil, Alia Maisara, Dia, and Zahra, me. So for the introduction, for reaction engineering 1, basically are we chose biomass as a source to produce syngas into methanol. And by using reaction engineering 1 concepts, we can figure out what design we should pick for the reactor and also calculate on what the best, um, how to get the best process basically. And um, biomass firstly, biomass is then gasified into syngas and then it's converted into methanol. So by using biomass, it's also a sustainable alternative to conventional fossil fuels or natural gases, and for methanol production. And then moving on to separation process two, methanol is a critical commercial chemical that's mainly used, and it can, as mentioned before, it can either be made from syngas or biogas. And the stream leaving the methanol plant has a higher concentration of methanol. So it's pure methanol, not pure methanol, but it has the high concentration of methanol, but it's still contaminated with water and other impurities. To achieve the industrial grade methanol purity of 99.5%, a robust separation unit is needed. Moving on to the design of reactor system. So first off, sustainability. Methanol is a really good clean energy source as it can um, release energy from being broken down. And also, it can by using methanol, we can mitigate carbon dioxide emissions or greenhouse gases because we're not using sources that release them into the atmosphere. And then biomass also uses eats up consumes CO2 emissions, which also reduces the greenhouse gas effect. And biomass also converts carbon dioxide into energy and stores it as hydrocarbons, further further emphasizing its sustainability. Now, energy requirement. Since we are using a catalyst, um, the activation energy needed is lower, so then there's less energy consumption as for the whole plant. And as calculated, the plant requires about 54.95 megawatts of energy. So for the technology maturity, biomass in itself has a low hydrogen content and high carbon dioxide content with about 6% hydrogen and almost 50% carbon dioxide, which is not the same as natural gas. Where if natural gas used in syngas, it will be it will be a better S value. Basically, the ratio will be better fitting to its the requirements of good methanol production. So then to increase this S value is either we increase the H2, we increase the hydrogen, or we decrease the carbon monoxide. So how we can do this is by picking a better gasifier design. We have to make sure we pick a good one and also a proper gasification agent. And moving on to the now lastly for the feedstock availability. Now based on the region it's sourced, it can vary the cost and how much you can buy it. So the factors affecting the quality of biomass is the nutrient availability, the crop rotation and seasons. All this affect on how good uh, biomass is. Not only this, but also if it's available or not based on let's say a place has a lot of agriculture activities, then we can easily then it can they can easily source have a huge source of biomass, whereas another place has limited agriculture lands or activities like that, then they will have less. So this basically means that non-renewable sources such as fossil fuels, the natural gas is the one that we use, are less dependent on region, which means if we were to change to biomass, it would be less feasible because of the restrictions.
Here we have the process flow diagram of our methanol plant. Our feedstock that we're proposing is biomass, which is agricultural waste. First, it will go into a dryer to reduce its moisture content. Then it will go through gasification, which includes pyrolysis to break it down into its organic compounds, and then it will go through combustion with oxygen to be able to produce carbon dioxide and carbon monoxide. Then it will go through the quench and scrubber to remove small particles like dust, and also to extract unwanted gases. Then it will go through the water gas shift reactor, where steam was also added to be able to get the correct composition of hydrogen and carbon monoxide. Then that syngas is fed into the methanol synthesis reactor. There's also an outstream of captured CO2 to further adjust the composition that we need. In the methanol synthesis, it would produce raw methanol, which will then be purified. In the purification, there may be unreacted syngas, which can be recycled back into the methanol synthesis reactor. After the methanol has been purified to its standard grade, it will go to the methanol storage. In the methanol synthesis reactor, there are three reactions that occur. For the two main reactions, it's carbon monoxide hydrogenation and carbon dioxide hydrogenation, where carbon monoxide and hydrogen react to form methanol. And as a side reaction, there's the reverse water gas shift reaction, where carbon dioxide and hydrogen can convert to carbon monoxide and water. The main reactions, the hydrogenation of the carbon oxides, they tend to be exothermic, while the reverse water gas shift reaction is endothermic. Also, as we can see in the reaction constant, the carbon monoxide hydrogenation and carbon dioxide hydrogenation have a lower activation energy than the reverse water gas shift reaction. For the conditions of our reactor, the temperature should be between 200 and 300 degrees Celsius, and for our pressure, it should be between 50 and 100 bar. The temperature, it's best to keep it low, as it will favor the reactions that have a lower activation energy, which is the carbon monoxide hydrogenation and the carbon dioxide hydrogenation. So more methanol will be produced. And also, having a lower temperature lowers the energy required to facilitate the reaction, so that is also less cost. For pressure, it's best to keep it high because it will shift the equilibrium to the side with less moles, which is the side where more methanol is produced. So our chosen temperature and pressure for our reactor is 250 degrees Celsius and 50 bar. For our proposed methanol annual production, we are assuming that that 16,000 tons of methanol is produced per day for 333 days in a year, which would total to 532.8 kilotons of methanol produced per year. So we convert that to its hourly production to be able to do the material balance. So 532,800 tons per year divided by 8,000 hours per year, which is about 333 days in a year. So that would be 66.6 tons per hour. Here we see the table of the feed composition into the methanol reactor. It consists of syngas, which is the CO, CO2, the H2, and also water and inert methane. And we can see that there's still that no methanol is present in the reactants. And then in the effluent, we can see that some of it converts to methanol. The mass balance is done to ensure that we are able to achieve 66.6 tons of methanol per hour. With our material balance, we are able to see the conversion of the carbon oxides. We get the total of the initial carbon oxides minus the final amount of carbon oxides divided by the initial carbon oxides, and we are able to see that 48.3% of the carbon oxides is converted. Then we can see the selectivity of methanol produced versus the non-methanol products, which we calculate by combining the carbon oxides, the hydrogen, and the water. And we can see that it's 0.5453, which is less than 1. So it's not as selective towards methanol. For our yield, which is the methanol produced divided by the carbon oxides that we used, it's 48.29%, which matches literature and industrial results. In order to determine the type of reactor for our methanol synthesis, we have to look at the conditions that the reaction has to happen in. The reaction occurs in the gas phase instead of the liquid phase, as there may be problems in catalytic deactivation. And also, since it's in the gas phase, it removes the possibility of using a continuous stirred tank reactor for this reaction. And the reaction will be done with flow, as it is a large scale production. It will also be done isothermally instead of adiabatically. It is also using catalyst, it's catalytic, so it would be pad to bed instead of a plug flow reactor. It also must be water cooled as opposed to gas cooled to increase the heat removal. And it's also done in series to be able to increase the conversion, and also to make up for how much methanol needs to be produced.
Moving on to the catalyst type. So the catalyst type that we used is copper, zinc oxide, and aluminum oxide. So why this catalyst exactly? First off, for the Cu, the copper in it, the copper ion, it acts as an active metal and it has a good performance for industrial scale. It's always used. And then for the zinc oxide, it's a promoter and it can increase the reaction rate a lot by simply adding it to the catalyst. It will go up to 3 times or more for the reaction rate and the activity. For the aluminum oxide, it's also a promoter, but unlike zinc, it is able to withstand high temperatures. So it can, since the plant that we're using uses high temperatures, it can withstand. It will not denature or become ruined.
Hello, my name is Aisha and I'll be presenting part 1 of separation process 2. Okay, so first of all, as you see from this table, this is the industrial plant-based methanol reactor outlet composition, which is from a data collected by Mirva Gili et al. 2019. So from this table, we can see that even though the crude oil has gone through a reactor, there is still a lot of other impurities that comes with the methanol. So along with methanol, there is water, carbon dioxide, hydrogen, carbon monoxide, nitrogen, and methane. The methanol is less than 10% of the entire composition. This is why we chose to go through a few separation processes before it can turn into the 99.5% that we want. So the purification sequence that we chose is first, from the reactor outlet, the stream goes to a cooler and flash separator. The cooler and flash separator can separate the vapor from the liquids because the natural gas is a natural gas, so it's in vapor form and it will go through the outlet, whereas the methanol and some dissolved gases as well as water will go through the down outlet. After the cooler and flash separator, it goes to a degasser stripper. This is mainly to remove the dissolved gases. But however, it doesn't remove the water. And since there's still quite a lot of water inside the methanol stream, that's why we also have to go through the adsorber. So the adsorption bed that we chose is made out of 3A molecular sieve. The adsorbent that we chose is zeolite 3A molecular sieve. This is due to the high adsorption speed as well as the size. The water molecules, which are much smaller than methanol, can go through the adsorbent. However, methanol is kept out. The zeolites also have a hydrophilic nature, which means it can easily absorb water. And in comparison to 4A and 5A, 3A has an easier time to regenerate. In terms of adsorption process conditions, a fixed bed adsorption system operated in a temperature swing adsorption with inert gas purge and pressure swing is proposed to ensure uninterrupted production. The parameters of temperature is at 25 degrees Celsius. This is to enhance mass transfer kinetics while keeping fluid viscosity low. The pressure is at 10 bar to make sure that the liquid doesn't turn into vapor, and the flow configuration is a downflow fixed bed to prevent bad fluidization as well as eliminate channeling. The adsorption mechanism is physical adsorption due to the difference in sizes, and the cycle time is at 8 hours because we want to synchronize it with standard 8-hour plant shift rotations and also provide ample time for regeneration.
Now we are going to calculate the estimation of required absorbent amount in the system. So we know that the total feed is around 162,000 kilograms per hour, mainly consists of methanol and water. After calculation, we obtain the purified product flow is around 137,000 kilograms per hour. Only around 700 kilograms of water per hour is allowed in the product. Therefore, about 24,000 kilograms of water per hour must be removed. Using the Langmuir equation, we obtain that the absorption capacity of zeolite 3A is around 0.19 kilograms of water per kilograms of zeolite. For an 8-hour cycle, the estimated adsorbent requirement is around 1 million kilograms of zeolite 3A. For the mass balance, each column removes around 170 kilograms of water per hour. Over an 8-hour cycle, this gives around 1,350 kilograms of water. Using the absorption capacity, the required amount of zeolite 3A is around 7,100 kilograms per column. For 4 columns, the total is around 28,400 kilograms. Next, the flow rate is converted into volumetric flow, which is around 44 cubic meters per hour. Using the selected superficial velocity, the required column area is around 1.2 square meters, giving an internal diameter of around 1.24 meters. Next, for the bed height, the saturated absorbent volume is around 10 cubic meters. From this, the saturated bed height is around 8 meters. After adding the mass transfer zone, the active bed height becomes around 9.6 meters. With a 25% safety allowance, the total column height is around 12 meters. Finally, the pressure drop is checked using the Ergun equation. The calculated pressure gradient is 0.0186 bar per meter, which is much lower than the allowable limit of 0.2 bar per meter. Therefore, the column is expected to operate with an acceptable pressure drop and safe.
I'll be presenting the regeneration strategy and operational mechanism. So the meaning of regeneration of bed basically means we restore the water saturated zeolite 3A sieve without damaging its crystalline structure. So the method that we use is temperature swing adsorption combined with inert gas purge and pressure swing adsorption. So the mechanism is we lower the bed pressure to around 1 to 2 bar to weaken the pressure between the water and the bed sieve, while simultaneously add nitrogen purge, hot nitrogen purge at around 200 to 260 Celsius to provide enough thermal energy to break the van der Waals force between the water molecules and the zeolite bed. We also flow the nitrogen gas countercurrent to allow the gas to sweep away the evaporated water that has been dissolved from the bed. So the steps are: number one, crude liquid methanol enter the chamber at around high pressure and low ambient temperature. And then we introduce PSA to weaken the polar bond between the water molecules and the sieve. Number three, we introduce hot inert gas purge nitrogen countercurrent from bottom to the top because PSA alone is not enough to break the van der Waals force between the water molecules and the sieve. So moving on to the strategy. So we implemented a two-bed system which operates on an alternating schedule. So what it means is basically while immediately after bed B finish its hot baking phase, we automatically start reconditioning of bed B. So the reconditioning of bed B happens when bed A is actively online. This ensures that bed B is fully cooled, repressurized, and waiting on standby before bed A becomes saturated with water. So the steps are: we introduce inert purge, which is cool nitrogen at around 25 to 40 degrees Celsius, and then we repressurize the bed to around 15 to 40 bar to allow bed B to go on standby mode. So the conclusion for reaction engineering is we use a isothermal backbed reactor with a copper, zinc oxide and aluminum 2 oxide catalyst operated at 250 degrees Celsius and 50 bar. We also use the 2 to 1 ratio for hydrogen and carbon monoxide to maximize the syngas conversion. We also managed to achieve a conversion of 48.3%, producing at around 66.6 tons per hour of ethanol, which yield around 48.29%. The conclusion for separation process, we use a fixed bed absorption column packed with zeolite A molecular sieve, followed by cooling, flash separation, and degassing column. The dimension for the column is column diameter is 1.24 meter. The bed height is 9.58 with a low pressure drop of 1.86. We managed to achieve around 99.5 percent of methanol purity via selective water absorption